numerical methods, the Newton-Raphson method. So to get a numerical solution to an equation of this form, so you basically take all of your terms to one side, so you've got 0 on the other side. You use this iteration formula. It's given in the formula book. There's a condition: the derivative f dash x cannot be equal to 0. If it's 0, you end up dividing by 0, which is going to cause problems. Okay, so graphically it works like this. So we've got some function of x here, and we have a root that we're trying to discover, and here is our initial guess at the root. So we go from our value of x to the curve, and you work out the equation of the tangent. It meets the x-axis at this point. We'll call that x2, and you'll see that x2 is an improved guess. We're getting closer to the root. So then you do the same again. You go from x2 to the curve, work out the equation of the tangent. The tangent will intersect the x-axis at this point. Let's call that x3, and again x3 is closer to the root, so our estimates here for the root are improving. You don't need to know where this formula comes from, but it has an interesting proof. So we start off with our function of x, and the coordinates for this point are x1, and the y coordinate is just the value of our function y equals f of x, so f of x1. The gradient will be f dash x, and the gradient at our point will be f dash x1. So we have the equation of a straight line, which is what the tangent is. So we have y minus the y coordinate is equal to the gradient times x minus the x coordinate. The tangent meets the x-axis, so y is equal to 0, so that term is 0, so it eliminates, and then divide by f dash x, and then rearrange, and this looks very similar to the formula for the Newton-Raphson method, this one. We just need to add the subscript n's and n plus 1, like this. So if we start with x1 as our initial guess, then this is x2, the improved guess. The method fails if the gradient f dash x is equal to 0 at any point. So let's imagine that this is part of a curve, and right here you draw a tangent to the curve, and you'll see that the tangent is horizontal because it's drawn to a stationary point where the gradient is 0, and this horizontal tangent will never meet the x-axis. The method relies on the tangent intersecting the x-axis. That's one of the reasons. The other reason is that if f dash x is 0, then you're dividing by 0 in this fraction, which you can't do. It gives you something that's undefined. Okay, so you're also dividing by 0 in the formula. So let's have a look at a quick example where we just come up with the iteration formula. So I've got an equation that I want to solve, so we're doing a numerical solution using the Newton-Raphson method. So we take everything to one side, and this is my function of x. So I need to differentiate, which I've done. So now we substitute everything into the formula. So you have xn plus 1 equals xn minus. That's the standard part of the formula, that's always there. And then you need your function of x, and here's our function of x. So that goes into the numerator, but modify all of the x terms to x sub n. And then we have the derivative f dash x, and our f dash x is here, and that all goes into the denominator here, again modifying x to x sub n. And here's the iteration formula that we would use. All we need now is an initial value that you put in for x, and on the calculator use the answer function just like you did with iteration earlier with the numerical methods, and that's all. So here's another example. We'll actually do the iteration this time. So f of x, f dash, and then we have our iteration formula. Okay, so my initial value will be 2, so that's x naught, and then you put 2 in here, you press equals on the calculator. My next value is here, and then you press equals again and again. So the solution is 1.856 to 3 decimal places. So I have to wait and see when my 4th decimal place is stable enough for me to round to 3 decimal places. For practice, try these questions.